Now, good morning, learners, and welcome to my lesson here. And I want to be taking you through the qualitative analysis. In my series, in one of my series on qualitative analysis, I must have mentioned here that we are going to have two types of qualitative analysis that we talk about in our high school. We talk about the inorganic. We talk about the inorganic. We also talk about the organic. And I must have said here that inorganic deals with the salts. It deals with the salts, while the organic will deal with organic compounds. Talk about the alkanes, the unsaturated hydrocarbons, the alcohols, the ROH, and alkanoic acids. Now, I want us to start maybe discussing something about the inorganic qualitative analysis, that where we will be talking about the analysis of salts. And of course, all salts, any salt will contain an anion and a cation. And in Form 2 we actually see that this cation could be a metal. It could be a metal obtained from actually a metal or a base, or it can also be an ammonium ion. So basically that's what we'll be talking about, and then later on here I'll also be talking about how we can be able to identify the anions. Now, in my first series here, I want to take you through some of the reagents that we use in the identification of cations. Identification of cations, because one of the strategies actually to be able to handle any practical and qualitative analysis, you've got to master the reagents, and of course you should have an idea of exactly what happens in these particular reactions. What is the chemistry behind some of these observations that we make? Now, I want to start with the sodium hydroxide. And sodium hydroxide here, we must have seen, or we must have come across sodium hydroxide. Now, when you think about sodium hydroxide, you should think of it being a strong base. It is a strong base. It's important to note that. That is where maybe that idea will be applicable. We are going to see it. Then number two, we also think about the hydroxide ions. Now, when sodium hydroxide here is in aqueous state, it contains hydroxide ions. And therefore, these hydroxide ions can form a precipitate. They can be precipitated by given cations. Remember, this one is negatively charged. We can have, if we have another cation, then they can come together. And if the hydroxide formed here is insoluble, it will obviously form a precipitate. It will definitely form a precipitate. That's what we're talking about. So let's get to the observation. Now, no precipitate formed. Now, when no precipitate has been formed, that should tell you here that the cation in that particular solution, the cation in the solution under test, is forming a soluble hydroxide. It is forming a soluble hydroxide. Please don't forget here that when you talk about a precipitate here, a precipitate refers to an insoluble salt in a solution. Actually, precipitates here, we can talk about this suspended particles. The suspended particles in a solution. That is what a precipitate is all about. Now, so let's see here. No precipitate formed here means that the cation that is there is actually forming a soluble hydroxide. Now, which are these soluble hydroxide? Now, one of the soluble hydroxide that we have here is potassium hydroxide. Therefore, I'm going to have potassium ions. Note the charge of potassium here is 1 positive. Now, sodium hydroxide as well. Sodium hydroxide here is soluble. It is actually soluble, and therefore it cannot form a precipitate. Then, of course, we also have the ammonium ions. Get note of that. Ammonium ions. Now, these are the only soluble hydroxides. The only soluble hydroxides that we have, or we can talk about, as far as our level is concerned. So basically, this is the way we inference here. If you realize here that you've added sodium hydroxide droplet is still in excess here, and no precipitate has been formed, then potassium ions, sodium ions, and ammonium ions could be present. Could be present. That's what we're talking about. Now let me get maybe to the second observation here. Now, an observation where a white precipitate has been formed and it is soluble in excess. Let's have a look at that. Now, for the formation of a precipitate in the first case here, in drop points here, that means that an insoluble hydroxide has been formed. An insoluble hydroxide has been formed. Now, the dissolving, because this is what we are saying, when you talk about soluble in excess here, means that the white precipitate formed here is actually dissolving in excess. What does this imply here? That one, an insoluble hydroxide will be formed, and this insoluble hydroxide here is further reacting with the excess sodium hydroxide. Now, a hydroxide here that reacts with this kind of hydroxides, and we know that hydroxides are actual bases. Any base that react with another base, we refer to them as amphoteric. They are referred to as amphoteric. Therefore, when you think about this here, a white precipitate forming here, and then the white precipitate, of course, is a hydroxide. Now, this insoluble hydroxide reacts further with the sodium hydroxide or the hydroxide ions and will form, the fact that it is dissolving, that means that it forms a complex salt here that is soluble. Now, in this particular case here, the amphoteric hydroxide, we think about the amphoteric hydroxides. Which are these amphoteric hydroxides? Now, the amphoteric hydroxides here, we have zinc hydroxide. Now, when zinc hydroxide is formed, if you put excess sodium hydroxide, it will react with it and form a complex ion of zinc. Therefore, zinc ions will be one of the probability, zinc ions. Now, another one here that is also amphoteric, another hydroxide that is amphoteric is that of aluminium. Look at that. Aluminium hydroxide is amphoteric. Now, the other one here, we're also going to have the lead. Lead hydroxide as well is actually amphoteric. Lead hydroxide is amphoteric. And therefore, if formed on addition of excess sodium hydroxide, the insoluble hydroxide reacts with excess hydroxide and you're able to form a complex ion. You're going to form a complex ion. Now, maybe for the sake of understanding, maybe let me just mention something about zinc here. If I talk about, for example, zinc, just to explain exactly what is happening here. Now, if I have something like zinc ions, if you add a few drops of hydroxide ions, it actually forms zinc hydroxide. Look at that. It forms zinc hydroxide. This is the white precipitate. The white precipitate. Now, this white precipitate, the white precipitate here, which is zinc hydroxide here, if you continue adding sodium hydroxide, the hydroxide ions further react. The hydroxide further react with the zinc hydroxide and form a complex ion, which is actually this one here, what we call tetrahydroxyl zinc 2 ions. Tetrahydroxyl zinc 2 ions. If you do that with you want to get that. This is the ion that you're going to get. This is the ion that you are going to get. Now, if you try to think about the salt, actually, this salt, the salt of sodium, we can call it sodium zincate. This one here, if this one combines with sodium ion from sodium zincate, that sodium zincate here is actually soluble. It is actually soluble. We actually know that all sodium salts are soluble. They are soluble. Therefore, if this one here will be formed automatically, our precipitate will actually dissolve. So others follows the suit. We are going to have aluminium again with reacting with hydroxide ions, forming aluminium hydroxide, reacting with more hydroxide ions and forming tetrahydroxyl aluminium 3 ions. Lead as well. That's basically what we are talking about. Now, let me give you some information about this here. A white precipitate forming, and it is insoluble in excess. Now, when you find that the precipitate formed is insoluble, that means here that the hydroxide that we are getting, number one, is insoluble. We are getting an insoluble hydroxide, And the insoluble hydroxide here is not amphoteric. It is not amphoteric. That means here that it cannot react further with the sodium hydroxide. Now, which are these? Which are these? Now, with this one here, we are going to have the magnesium ions. Look at that. We are going to have magnesium ions. Now, magnesium ions, the hydroxide of magnesium hydroxide is not amphoteric. It is not amphoteric, and therefore it will not dissolve upon addition of more sodium hydroxide. Now, I can also maybe mention about the calcium ions. I can also mention about the calcium ions. So these two here are the likely ions when this one happens here. Now, maybe one more thing here that maybe if you want to remember this, here, why can't you just have this one here and talk about the ZAP here? Look at that. You can just remember the ZAP. You remember something like ZAP here for amphoteric hydroxide, you can easily remember that. For magnesium and calcium here, you realize that these ones are group 2 elements. You can maybe think about that. These are group 2 elements. Of course, I've been mentioning about, in one of my series, I've been talking about the periodic table. You've just got to look at the group 2 here, the magnesium ions and calcium ions. Now, when you're using the sodium hydroxide as well, it's important to note here that you can also be able to you can actually be able to have colored precipitates. It is important to know that. You can actually be able to have colored precipitates. Now, for colored precipitates also, it is important to note that also we have their solution. Their solution are also colored. Their solution are also colored. This is important. It is important to note that here, that their solutions are also colored. So therefore, most of the time here, if you happen maybe to dissolve a salt and you realize here that the solution form here is colored, then you can easily identify the cation. You can easily identify the cation. Most of the colors that you get here, we have blue, we have green, and a brown, sometimes yellow when it is a solution, when it's yellow when it is a solution. A blue precipitate is insoluble in excess. Now, this one here implies that copper ions are present. Copper ions are present. And therefore, maybe during that electrolysis, not electrolysis, sorry, but during the analysis of this, whenever you realize that you maybe have formed one, to maybe a blue solution, and then on addition of sodium hydroxide, you get a blue precipitate that could be copper ions. A green precipitate forming here, automatically this one will be the iron 2 ions. The iron 2 ions. That's what we're talking about. A brown precipitate. A brown precipitate here. Now this one here will be iron 3 ions. Look at that. Iron 3 ions. So this ion here, it has the 2 oxidation states. One of them is iron 2 positive, and it's important to note here that to convert iron 2 positive to iron 3 positive here, you've just got to use an oxidizing agent. An oxidizing agent that will be able to remove an electron from iron 2 ions so that it will just form iron 3 ions. An example of this here, for instance, you can use something like hydrogen peroxide. Hydrogen peroxide, you can actually be able to use it. If you use hydrogen peroxide with an oxidizing agent, you'll just be able to form iron 3 ions. What does that mean? If you actually get a green precipitate, and then on the green precipitate, you add hydrogen peroxide. Look at that. Add hydrogen peroxide. You're able to get a brown precipitate, which is actually the iron 3 salt. You can actually be able to remember this one here with the rust. The rust. When it comes to the rust here, the iron, when corroded, it forms a red brown substance there. You can easily remember that. Please, this is something that we must all get. Now I want to discuss now the ammonia. Remember, we're going to look at these reagents. At the end of the day here, I'll be able to analyze. We'll be asking ourselves, how can we analyze? How can we test for aluminium ions, for example, the magnesium ions, and so on and so forth. Now, let us look at maybe the second reagent, which actually happens to be ammonium hydroxide. Now, ammonium hydroxide is also aqueous ammonia. Aqueous ammonia. Now, ammonium hydroxide, as you can see here, it is a base. The mention of hydroxide ions, of course, just tells you here that this one is a base. However, it's important maybe to mention here that there's a difference actually between ammonium hydroxide and sodium hydroxide that we just mentioned here, because ammonium hydroxide is a weak base. A weak base means that when this ammonium hydroxide here, in solution form or in water here, will dissociate or will ionize partially. That means here that maybe only hydroxide ions will be produced as it dissolves in water. That's the difference here. But when you compare it with something like sodium hydroxide, for sodium hydroxide here will actually release so many hydroxide ions. Therefore, we are going to expect some differences as far as this one is concerned. Now, it's also maybe important to mention here that when you talk about the amphoteric hydroxides, it's important to know that here, amphoteric hydroxides here will only react with the strong bases. That's another difference that we're going to meet with this here. We saw it in sodium hydroxide, that for example, the zinc hydroxide, the lead hydroxide, and the aluminium hydroxide. Those ones can react with excess sodium hydroxide, but this one being a weak base here, we may not expect the same. So let's have a look at what we're talking about. Number one here, no precipitate formed. No precipitate formed here means that the cation that is in the solution under test here does not form an insoluble hydroxide. In other words, the hydroxide here of that particular cation there is soluble. Now, which are these? Of course, we mentioned about the potassium. We mentioned about the sodium ions, that is in sodium hydroxide there. They were still there. And I also talked about ammonium ions. Now, maybe another one that we're going to add on top of this here is actually calcium ions. Calcium ions will also be there. We can also mention about the barium ions. Now, what happens here when we add in calcium ions and maybe barium ions, because they are hydroxides. Here. Remember, I've just mentioned here with ammonium hydroxide here, being weak bases, they are going to release very few hydroxide ions, and therefore the calcium hydroxide form in this particular case here will be small, which is actually able to dissolve. Will actually be able to dissolve. Therefore, this one here will dissolve, and the barium here hydroxide will also be able to dissolve, again because only a little quantity of it will actually be produced. Therefore, a difference between ammonia and sodium hydroxide here, you can realize here that we are adding calcium ions and barium ions. Let me talk about the second one here. A white precipitate formed, soluble in excess here. And I've just said here, when it comes to this here, this may not necessarily be the reaction with hydroxide ions. It may not be. It is actually not a reaction with sodium hydroxide because the ammonia solution is a weak base. It is actually a weak base here. Now, so this one here, why this one happens here is due to the formation of a complex ion which actually forms a soluble salt. So in this particular case here, we are going to have the zinc ions. Kindly note this here, that this property here of this ammonia forming a complex ion with zinc ions here, it makes the test of zinc ions very simple. When I want to test for zinc ions, I can actually go for ammonium hydroxide. I put it in dropwise still in excess. If a white precipitate is formed, soluble in excess, that one actually confirms it's zinc ions. Now, what happens here? Maybe I can do some explanation here using ionic equation here. Now, zinc ions in the first case here, if you put this ammonium hydroxide, is able to release the few hydroxide ions there, and will be able to form the zinc hydroxide. Here, which is actually a white precipitate. This is a white precipitate. Now the zinc hydroxide here, let's see how the complex ion is formed. Now here we have talked about the ammonium molecules in my ammonia solution there, and what will happen here is that we are going to form a complex ion here. Now, which is this complex ion? We are going to call it tetraamine zinc 2 ions. Get note of that. Tetraamine zinc 2 ions. Now this one here, you're going to have 2 positive. Maybe I can mention here that this ammonia molecule here has a 0 charge. It has a 0 charge here. That means 0 times 4 is still a 0. And therefore this ion will acquire the charge of zinc, which is actually 2 positive. You can actually be able to tell that. Then from there, of course, the hydroxide ions here in my zinc hydroxide will be released here. Then I'm going to have the hydroxide ions. Of course, I can just balance by putting that one there, and that is what we're talking about. So a precipitate forming here, the precipitate is actually zinc hydroxide. When it dissolves in excess here, this is the ion that I'm talking about, the complex ion here, tetraamine, 4 amines, tetraamine, zinc, 2 ions. That's what we're talking about. Now this one here explains why the precipitate of zinc hydroxide here will dissolve in excess ammonia solution. That's what we're talking about. Let's get to the second here. A white precipitate formed insoluble in excess. Insoluble in excess. Now, of course, here this we're going to talk about the hydroxides that are almost insoluble. That means that once these hydroxides are formed here, even if maybe they are going to dissolve, maybe they dissolve very their solubility is very low, such that still a precipitate will still remain. Now, which are these? I'm going to have magnesium ions. I'm going to have magnesium ions. Get note of that. I'm going to have aluminium ions, and I'm also going to have the lead ions. I want you to get that. Remember, for aluminium and lead here, when we were dealing with the sodium hydroxide, when we were dealing actually with a sodium hydroxide, we noted that aluminium and lead, remember the ZAP, the aluminium, lead, and zinc here, these ones would dissolve in excess sodium hydroxide. Now see the difference here. For aluminium hydroxide and lead hydroxide here, they will not dissolve because, of course, this ammonia here is a weak base, therefore they may not be able to react with the excess hydroxides. Now for magnesium here, again, it appeared somewhere, it will not dissolve again in sodium hydroxide, but they were also alongside calcium ions. See now where the calcium ions is. Because the calcium hydroxide here is more soluble. It's actually more soluble compared to magnesium. Go back to the period, to the group 2 here, and note something here, that the solubility of these hydroxides here, down the group, their solubility increases. For magnesium here, its solubility here is lower than calcium. From calcium, you go to barium, their solubility increases down the group. That's what we're talking about. Now, a blue precipitate dissolving, forming a deep blue solution. This one is another observation that we expect. A blue precipitate dissolves, forming a deep blue solution. Now, this one here again will be copper ions. Mostly when you're dealing with the blue solution here, it is always good to suspect that copper ions could actually be there. Copper ions could actually be there. Now, again here, the idea here is not necessarily about the amphoteric. It's actually again about the formation of a complex ion. The formation of a complex ion. Now, this one here is very similar to what we have in zinc hydroxide. Actually, we're going to have something like this here. I'm just going to make some more, whatever. I'm going to have the copper ions. Copper ions plus hydroxide ions will form a blue precipitate, and the blue precipitate here is copper hydroxide. It's actually copper hydroxide. Now, this copper hydroxide again here, we can replace here zinc. We're going to have copper hydroxide reacting with the aqueous ammonia here. When it reacts with aqueous ammonia here, we are going to form tetraamine copper 2 ions. Look at that. Tetraamine copper 2 ions again with a charge of 2 positive, because this ammonia here has a 0 charge here. There's ammonia molecules here. 0 times 4, you get a 0. Then this one has 2 positive, therefore the overall charge of the ion has 2 positive. So this is what we're talking about here. Again, tetraamine copper 2 ions. Copper 2 ions. Now this one here, its color is deep blue. Look at that. Its color here is deep blue. That's why for copper hydroxide, of course, here, this one is a blue precipitate. It's a blue precipitate, and the blue precipitate here, upon addition of excess ammonia solution, you form a deep blue color of tetraamine copper 2 ions, which is deep blue. That's what we're talking about. Now I take you there to the green precipitate. Now that one again is iron 2 ions. Why this one happens again? The iron hydroxide is the iron 2 hydroxide is actually green. The iron 2 hydroxide is actually green, and it does not form in a complex ion with excess ammonia, therefore it will not dissolve in excess. Then a brown precipitate again, insoluble in excess. That one again we talked about, the iron 3 ions. Some similarity that you can actually be able to see here. The iron 3 ions, iron 2 ions, This one is similar. Copper ions, you can see blue precipitate. The only difference here when it comes to sodium hydroxide, it does not dissolve in excess because it does not form actually a complex ion. It does not form a complex ion. And that's what we're talking about as far as ammonium hydroxide is concerned here. Let me get to the third reagent. Now, the third reagent here, I want to talk about the sodium sulfate. Now, as far as the sodium sulfate is concerned here, this one is actually, or will work on the basis of solubility, or what you call a precipitation reaction. Now, if you happen to introduce the sulfate ions to any solution, if a white precipitate is formed, that means that that cation is forming an insoluble salt with a sulfate. Now, which of these sulfates are insoluble? Which of these sulfates are actually insoluble? Therefore, I'm going to have lead ions is one of it because the lead sulfate is insoluble. I'm going to talk about the calcium. I'm going to talk about the calcium sulfate. Now this one here again is insoluble, those sparingly soluble. Then finally I'm going to have the barium. I'm going to have the barium ions. Now these three here are actually insoluble. They are actually insoluble. Now when you're working out this qualitative analysis, you must not always get positive observations. The time you get negative, for example, no white precipitate formed. Of course, this would mean here this are present. Now when you don't form a precipitate, of course, that means that these ions here are absent. That is what we are talking about. That is what we are actually talking about. So this one is just about the solubility of sulfate, and conclusively we can say that all sulfate, in order to form two salts here, all sulfate are actually soluble, except that of lead, calcium sulfate, and barium sulfate. So this one is purely on this principle. It is purely on our principle here that all sulfate are soluble except the lead sulfate, the calcium sulfate, and the barium sulfate. That's what we're actually talking about. Now let's talk about the sodium chloride as a fourth reagent that we're talking about here. Now again here, this one also has to do with the precipitation reaction. And what we're supposed to ask ourselves, which of these chlorides are actually insoluble? Because if they are soluble, of course, that's when you're going to form a white precipitate. Now, one of them, of course, here we have to know that all the chlorides here are soluble with an exemption of lead chloride and silver chloride. Therefore, that means here, if you're going to form a white precipitate here, that means that the chloride ions have formed an insoluble salt with either the lead, look at that, you have the lead ions or silver ions. Of course, if no white precipitate is formed, as we have just seen here, so this one means that the two are present. If no precipitate is formed here, of course, that means also that the lead ions and silver ions are absent. Yes, and that is what we are talking about. That is what we are actually talking about. Now, maybe we can discuss up to that point, but let me also mention maybe of another reagent that we commonly use here, and water. Now, reagent 5, let's talk about the potassium iodide. With potassium iodide here, when you put a potassium iodide in a solution, you may expect a yellow precipitate. Now, when you see a yellow precipitate here, the ions here that can actually form a yellow precipitate with iodide ions, we have the lead ions, because the lead iodide is yellow. We also have the silver iodide, which is also yellow. That means that the potassium iodide here, you may not be able to confirm. You cannot confirm it. You cannot confirm lead ions or silver ions on its own. I think you have to make, or you have to do some other test to be able to confirm it. Now, the other one here that I must talk about here is distilled water. Now, distilled water here, now this one is common in both the test of anions and cations. Remember, when you're dealing with, in this qualitative analysis here, we deal with solutions. We actually deal with the solutions because solutions have ions, but in solid state, these ions are not mobile. Now, when you are adding a solid, when you add distilled water to a solid, the expectations are, number one, a solid dissolves and forms a colorless solution. Solid dissolves and forms a colorless solution. What are the inferences for this? Now, one, for the solid dissolving here, that means that we are going to have a soluble salt. The salt that you're dealing with here is soluble. So we have soluble salt present. Now, when you form a colorless solution, what does that mean? It means here that colored ions are absent. The colored ions are absent. Which are these? You could have copper ions. Now, a solution of copper ions is actually blue. It's actually blue, or you can talk about the pale blue. Now, talk about iron 2 ions. Now, solution of iron 2 ions is normally pale green. And finally, the solution of iron 3 ions is actually yellow. That is what you're talking about. That means here that maybe besides the what I've just mentioned here, you can also, the solid can dissolve and form a blue solution. If it forms a blue solution, of course, copper ions could be there or could be present. If it forms a pale green solution, that means that iron 2 ions could be there. If it forms a yellow solution, then iron 3 ions could actually be there. That's what we're talking about. Now, number 2 here, a solid may dissolve partly. Where you realize that a solid has, in a way, the amount of solid that was there actually has decreased, though there is some that remains. There is some that remains. Now, in most cases here, when you see such, this could actually mean here that the solid that you have been given here is a mixture of soluble and insoluble salt. That's what it is, a mixture of soluble and insoluble salt. Now, in most of these cases here, during these practicals, at times you may be required here to filter. You may be required to filter. And when you're filtering here, always you can comment about the color of the filtrate and the residue as well. That is what we are talking about. If not this, we can also have the solid partly soluble. There are some salts that you're going to deal with here whose solubility is low. The solubility is quite low here. So if the solubility is low, then you may expect that some of it does not dissolve and some of it dissolves. So basically that is what we are talking about as far as our reagents are concerned pertaining cations. Now we can use even more, we can have more, but maybe these are the major ones. And what I'm going to do now is to try, and I want to maybe assist you maybe in what we call the analysis. I want to give you some what we call analytical skills here that we can actually be able to use to identify a given salt. So we're going to have a question here, and this question here we should be able to identify. We think of the reagents that we're going to use, or I can actually be able to give you some reagents, and then we try to argue it out. How can we be able to test or to confirm certain ions in that particular solid? That's what we're talking about. Now, let's have a look at maybe, or we try to apply what we've just learned about our reagents here. I've just mentioned a bit about we're going to use some of them here to help us analyze a given salt suspected to contain aluminium ions. Now, so we're going to use sodium hydroxide, we're going to use ammonia, we're going to use sodium sulfate. Now, we can maybe use, you can start with sodium hydroxide. We can also use or we can start with ammonia and then we move forward like that. Now, my main aim here is just to show you how to go about the analysis, just to give you some small analytical skills on this. Now, so let's start by using sodium hydroxide here. And remember, I'm talking of a solution. If I would be talking of a solid, I would first of all dissolve it. I would first of all dissolve a solid to form a solution. Now, so I'm going to start here by saying divide the solution into 3 portions. Look at that, into 3 portions. Into 3 portions. That's my first procedure here. Now, number 2 here, to the first portion, I'm going to add sodium hydroxide here. I'm going to add sodium hydroxide dropwise till in excess. Look at that, till in excess. Now, what observation do I expect? The expected observation. Remember here, I'm talking about aluminium ions. Now, if you remember what I mentioned about aluminium ions here, is that the aluminium hydroxide is amphoteric. And therefore, my expected observation would be a white precipitate here, soluble. Look at that, a white precipitate soluble in excess. Now, this one would not confirm. Let's look at that. This one would not confirm the presence of aluminium ions. It will not confirm the presence of aluminium ions because this one here, the alternatives can either be zinc ions, aluminium ions, or lead ions present. Lead ions present. Look at that. So I must think of a way, and this is where we were talking about the analytical skills. How do I eliminate the zinc and lead ions? How do I eliminate the zinc and the lead ions? Look at that. So I can come here and I mentioned something about zinc. There's something special about zinc and ammonia that I can be able to eliminate or confirm zinc ions using ammonia solutions. Let's have it. Let us have it there. Now, so I'm going to have 3 here to the second portion. I'm going to add aqueous ammonia, and this one again will be dropwise till in excess. Look at that, till in excess. Now, what we're going to observe here is, or what we expect to observe. Remember, I mentioned about aluminium and how it behaves with ammonia. The ammonia in this particular case here will dissociate partially in water and form ammonia and form some hydroxide ions, and therefore this hydroxide ions will form a precipitate with aluminium hydroxide, and this hydroxide, remember, does not dissolve in excess. Therefore, what I expect here is a white precipitate insoluble in excess, or which does not dissolve in excess. Look at that, which does not dissolve in excess. Now, in this particular case here, remember we mentioned here when you have such ammonia, you'll mention about the map. Either magnesium ions can be there, the lead ions can be there, or aluminium ions can be there. But you already here know that maybe from the first procedure, maybe you could have seen actually here that I'm either having zinc, aluminium, or lead. Therefore, when you're analyzing such a thing here, you cannot come here and mention about something like magnesium ions. You cannot mention about magnesium ions and the like. So instead of, because we're supposed here to put either magnesium, aluminium, or lead, you'll only put aluminium ions or lead ions present. Remember here, this is normally our marking point. This is normally our marking point. This also means here that zinc ions are absent. Because if zinc ions would be present, we would form a precipitate which would dissolve in excess. But the fact that the opposite happened, then that means zinc ions is absent. And when zinc ions is absent here, now I remain with aluminium ions and lead ions. Now we only have aluminium ions and lead ions. I only need to have a case near where now I can be able to eliminate the lead ions so that I confirm aluminium ions. How do we eliminate lead ions? I did mention about the sodium sulfate. If you recall here, we said that this lead sulfate is insoluble. Lead sulfate is insoluble. Therefore, I can use sodium sulfate to eliminate lead ions. So I'm going to have here to the third portion, I'm going to add a few drops of sodium sulfate. Now, if I'm expecting aluminium ions, that means here no white precipitate will be formed. No white precipitate formed, right? Because aluminium here do not form. Aluminium ions cannot form a precipitate with sulfate ions. But lead will do so. Now, so the fact that no white precipitate is formed, that means that lead ions are absent. Remember, lead ions will be absent, and what remains is actually aluminium ions. Present. That's what we are talking about. Therefore, those three procedures here, that's adding sodium hydroxide, I get the ZAP. Zinc ions, aluminium ions, lead ions are present, and then the other procedure, I will be using those reagents that can be able to eliminate either of this. I'm going to use, for example, ammonia to eliminate zinc ions, so that I remain with aluminium and lead ions. I'm going to use sodium sulfate to eliminate lead, so that I'm left with aluminium ions. So basically, this is what we are talking about. Now, in our qualitative analysis, what will happen here is that examiner here, or the examiner here, will expect you to use analytical skills, so that in the beginning of the practical here, you can have a number of ions, and then other procedures will be meant to eliminate some of those ions, so that in most of the cases you remain with one. And therefore, whenever you're given a reagent, think about this reagent is meant maybe so that I can be able to eliminate one or two things. This is what we are talking about. So I think in my second series here, I'll also be taking you through the analysis or the identification of anions. Again, so that at the end of the day here, we should be able to think about a salt. When you're given a salt, and then you should be able to identify that salt by looking at the anion part and the cation part. So I think that marks the end of my first series again here on qualitative analysis theory, and that is the inorganic part. And what I may just request of you here, kindly subscribe to my channel, like, share, and I will be grateful. Otherwise, thank you very much, and God bless.